So we've talked before about the Hartree-Fock limit, and can we reach it? Well, in practice, we can't because we're always using an incomplete basis set. So we don't have the ability to use an infinite basis set. Now, because of that, we want to use the best possible incomplete basis set or approach to dealing with this. Now, in practice, it turns out that the end of the fourth increase in the computational effort ends up limiting most calculations to hundreds or a few thousand basis functions. You can go larger, but a lot of calculations, that's going to be about the limit we want to use. Now, the thing is, if you use an basis set that only has a few hundred or a few thousand basis functions, you actually end up finding that the absolute errors in the energy compared to the lowest possible variational energy that you could get, just due to the basis set incompleteness, can be pretty large. So it can be several Hartrees, or in other words, thousands of kilojoules per mole. But of course, absolute errors aren't necessarily what we're looking for. We're really trying to get relative energies correct. And so we want to make sure we get our relative energies correct. Now, there are a lot of things we'll need to think about when we try to get those relative energies correct. Certainly one thing that we have to think about is the fact that we have to always use the same basis set when we're comparing energies between different species in a reaction or along the potential energy surface. We don't want to compare two very different quantities, such as apples and oranges. So in other words, you do have to make sure that you don't use even two different double zeta quality basis sets, like the 631G or the Dunning polarized valence double zeta. So it doesn't really make sense to compare those energies. All right, so we want to get the relative energies correct. What can we do to get the best accuracy for the least computational cost, or again, the least amount of computational effort? Well, one thing we can do is to examine where our results converge. So we'll just take, for an example, water with some different consistent basis set families. So I've got the Denning style basis sets over here, and then we've got the PC family over here. What we can do here is compare the water geometry. The water geometry has a certain bond length, 0.9578 angstroms, and an angle of 104.49. That's experimental. Now, what we can do is we can determine that at the Hartree-Fock limit, what are these values? So for example, we can take a look at the OH bond distance as the basis sets change. We can take a look at the HOH angle as, again, the basis sets change. We see that as we get even just to the quadruple zeta basis set, our value doesn't change afterwards. Our angle has mostly converged by the time we get to that quadruple zeta basis set. It's really converged by that quintuple basis set. So we can really say that that's converged by then. For the PC N basis sets, we can see the PC0 is very far off. PC1 is still off. PC2 is pretty close, and then PC3 and PC4 are both pretty converged. And if we compare between, say, PC3 and the quintuple zeta from over here, we can see that they get the same bond distance, they get the same bond angle, at least to 2 decimals. So we've pretty much converged our results at this point. Now, if we compare though to the experimental, we'll see that the Hartree-Fock bond length is too short compared to the experimental, and the angle is too large compared to the experimental. And this ends up being due to an overestimation of the hydrogen-hydrogen repulsion. So we're going to actually have to go beyond Hartree-Fock. Now, we have, though, with these basis sets, been able to reach the Hartree-Fock limit. Again, Hartree-Fock is not going to be the be-all and end-all of our methods, but at least we now know that as far as our basis sets go, we've reached the Hartree-Fock limit. We don't need to go to better and better basis sets. Now, when we do this kind of an approach, we can also do something else, and we can extrapolate to something called the Hartree-Fock limit. Now, with this kind of an extrapolation, we can take points. For example, we can take the value at double zeta and a value at triple zeta, maybe also a value at quadruple zeta. And we can take these 3 points, fit it to a curve that's a function of n to the minus 1, where n is the level of our basis set, double 2, 3, 4, for example. And we can extrapolate then to an infinite basis set limit. And there are a variety of different extrapolations you can do. You can do the one that involves the double and triple zeta points. It's maybe not as accurate as if you can do the triple and the quadruple. Maybe you can do the double, triple, and quadruple. Sometimes you can go up to higher, just depending on the system that you're dealing with. But anyways, again, your goal is to extrapolate out to this infinite basis set limit, which is also called the complete basis set limit. So of course, there are a few difficulties with this kind of an extrapolation. One question is, what is the form of the curve that one should use? So there are a variety of different curves that are used. Another question might be, should you optimize the geometry for each basis? Should you use the experimental geometry? What geometry should you use? You're just extrapolating the energy in this case. So, but it is something that people do often, especially for smaller molecules, is extrapolate out to this Hartree-Fock limit or to the complete basis set limit. Another type of way of getting to better and better basis set quality would be to use something called an additivity assumption. The idea is that we'll be able to add together different energetic contributions from different types of basis functions, and that they're not interdependent, that we'll be able to kind of separate these out. And so what this means is that, let's say we were wanting to calculate the energy at the Hartree-Fock level of theory using this triple zeta basis set, 6311G, and we wanted to have polarization functions and diffuse functions for this system. Well, the additivity assumption says, let's say we started off with a base of a 631G, which is a very basic double zeta basis set. And we added on, we're going to add on a correction. That's the difference in energy between a calculation that's done with polarization functions and one that's done without, to essentially get the energy coming from the polarization functions. Then we'll add on a correction term. That's the difference in energy between the triple zeta version, 6311G, minus this double zeta basis set here. So this will essentially get us to the triple zeta basis set. Where here we could look at what's the effect of adding diffuse functions compared to our basic double zeta basis set. And the idea is that these 3 contributions, if we added up all of those delta E's, added them onto this basic energy, that it's going to be approximately the same as if we'd done everything together. Now, it might seem like this is more work because we're suddenly having to do a lot more individual calculations. But it turns out that you actually have a lot fewer basis functions that you need to think about in any given calculation. So for our 631G calculation, there are 204 basis functions on an example molecule. If we add polarization functions, that jumps up to 294. If we were to go to the 6311G but no polarization functions, that's also 294 functions. If we were to add diffuse functions to S&P, that's 378. Again, those diffuse functions can really add up in a hurry, especially on the hydrogens. So those are the 4 calculations we potentially have to do. Whereas if we did one calculation with the full basis set, that's 542 functions. So initially it might not seem like, well, 4 calculations with this many functions compared to 1 calculation with this many. This is where you have to remember that these integrals go up as n to the 4th. So we have 1 calculation that's 204 to the 4th, one that's 294 to the 4th, another 294 to the 4th, and one that's 378 to the 4th. Basically 37 billion calculations. Whereas 1 calculation with 542, that's 86 billion integral evaluations. So it's about a little over twice as much. So you can certainly save time even by having to do 4 separate calculations. Again, that's an assumption that these different contributions can contribute different amounts to our energy stabilization. Now, another thing we need to think about when we're dealing with incomplete basis sets, which of course is all the time, is that we end up getting an error. Especially it shows up when we're dealing with complexes like this little water dimer shown here. So an energy of complexation could be written as the energy of the dimer minus the energy of one monomer minus the energy of the other monomer. Where the incomplete basis sets end up showing up is that the basis set for the overall complex is larger than for molecule A or for molecule B. Basically, what's going on is that molecule A can actually borrow some of molecule B's basis functions in order to make its energy a little bit lower. And molecule B can borrow some of molecule A's to make its energy lower. And then overall, that leads to an artificial energy lowering. And so the strength of the bond ends up being overestimated. And this is called basis set superposition error, or BSSE. Problem is, we know that there are some real physical effects going on. So these do interact. There are some charge transfer interactions and charge polarization effects that do take place. And so we know that there should be some interaction energy, but how do we determine how much that is? So there's an approximate way of correcting for the basis set superposition error. That's called the counterpoise correction. And what it basically does is it adds some extra basis functions that are called ghost orbitals. So when you're calculating molecule A, you would add in basis functions over here and figure out how much would that lower the energy. And when you're calculating the energy of B, you'd also add up some basis functions that were centered over here. That way that one can use those basis functions anyways. And so that'll account for that basis set borrowing. But this counterpoise correction isn't perfect, and sometimes it'll actually make things worse than the non-corrected energies. But at least it is one way of thinking about correcting basis set superposition error. Now, another way of working with basis set superposition error is to just go to larger and larger basis sets and see if your results converge. Larger basis sets are going to have less basis set superposition error because the molecules already have a lot more basis functions, and so they're therefore able to make their molecular orbitals better, their wave functions are better, that means their energies are better, so they'll tend to have less BSSE. And of course, an infinite basis set would have no BSSE.